spherical refracting surfaces. It is nothing but refraction at spherical surfaces. A spherical refracting surface is a part of a sphere of refracting material. A refracting surface which is convex towards a rarer medium is called convex refracting surface. A refracting surface which is concave towards a rarer medium is called concave refracting surface. That means here we have two refracting surfaces, one is convex and the one is concave. Now you can see both the surfaces here. This is convex refracting surface, this is a concave refracting surface. Now if you see, here it is acting as rarer medium because it is kept outside, and this is inside the spherical surface, so which will act as a denser medium. Now here for the second one also, this is rarer medium which is kept in air, and this will act as a denser medium. That is the principal axis. And if you consider the points, one is the optic center and the one is center of curvature for both the surfaces. So if you consider AB as the principal axis, P will act as a pole or optic center and C will act as center of curvature. Now the distance between the pole and the C, that is center of curvature, is called radius of curvature. Assumptions. Object is the point object lying on the principal axis. So whatever the object which you are going to consider, its size is considered as just like a point, so it is called as point object. Always it will lie on the principal axis alone. The incident and the refracted ray make small angles with the principal axis. So this is the second assumption. That means the angle of incidence as well as the angle of refraction will be very less. The aperture, that is nothing but the diameter of the curved surface, is taken small. Cartesian sign convention. So what sign convention steps which we are going to consider here while studying the refraction at spherical surface? The incident ray is taken from left to right. So always the incident ray moves from left side to right side. That means from your left hand side to right hand side. All the distances are measured from the pole of the refracting surface. So here pole will act as origin. The distance measured along the direction of incident ray are taken as positive and against the incident ray are taken as negative. That means if you start from pole, if you are moving along the direction of incident ray from left to right, it is positive. From pole, if you are moving from right to left, it is taken as negative. The vertical distances measured from principal axis in the upward direction are taken as positive and the downward direction are taken as negative. That means above the principal axis, all the distances or heights are taken as positive. And below the principal axis, it is taken as negative along the vertical direction. Now we will study about how refraction at convex surface, that is from a rarer medium to denser medium, takes place for a real image. I am going to consider the convex surface, that is the rarer medium, and this is the denser medium. Let the refractive index of the rarer medium is taken as mu1 and the refractive index of denser medium is taken as mu2. This is the center of curvature and P is the pole, that is principal axis. Now I am going to consider a point object, let it be O. Now this is how the ray is going to incident. This is the blue ray is considered as the first ray and it gets refracted and it is going to incident at this particular point on the principal axis, which is taken as I. The second ray is passing through the principal axis and this is called normal incidence, so it will go undeviated and both the refracted rays are going to meet at this particular point, which is taken as image. Now here, as the refracted rays are meeting, converging it is taken as a real image. Let n be the normal and A is the point of incidence. Now if there is no convex surface, how the ray will pass? The ray will pass in a straight line. Now the angle made by the incident ray with respect to normal is taken as angle of incidence. And if you draw a perpendicular and this is M, generally as the angle is small, the curved surface is taken as a plane surface, like a straight line. Now this is the refracted ray which is making an angle R with respect to the normal. It is taken as angle of refraction. Let the incident ray OA makes an angle alpha with respect to principal axis. The refracted ray makes an angle beta with respect to the principal axis. And the normal makes an angle gamma with respect to the principal axis. So always you have to consider three angles. One, incident ray making with the principal axis, refracted ray making with principal axis, normal making with principal axis, alpha, beta, gamma. Now R is a radius of curvature here, and U is the object distance and V is the image distance. Now if you see the triangle OAC, if you consider this triangle OAC, I repeat, I is the exterior angle for this triangle. So always the exterior angle is equal to the sum of two opposite interior angles. So I is equal to alpha plus gamma. This is the first step. In the same way, if you take the triangle IAC, I repeat IAC. If you consider the triangle IAC, gamma is the exterior angle and R and beta are the two opposite interior angles. So the second equation is gamma is equal to R plus beta. That is your second equation. Or we can write R is equal to gamma minus beta. Now take tan alpha. So if you consider the triangle AOM, I repeat AOM, it is a right angle triangle. I want to determine tan alpha. Tan alpha is nothing but what? Perpendicular by base only now. So AM or MA divided by MO. Or if you take the angles as small as per the assumption, alpha can be written as MA by MO. Similarly, if you consider the triangle again AIM, it is a right angle triangle. Again, if you take tan beta, perpendicular A or MA by MI, as the angles are small, beta equal to MA by MI. Similarly, tan gamma, if you take the triangle, right angle triangle ACM, so it is again MA by MC, or gamma equal to MA by MC. Now we have the three values alpha, beta and gamma. According to Snell's law, what is Snell's law? Sin I by sin R is equal to mu2 by mu1. So if you consider this, or I by R equal to mu2 by mu1. For small angles, I repeat, we are going to consider sin I as I, sin R as R. Or mu1 I is equal to mu2 R. Substituting for I, R, alpha, beta and gamma, replacing M by P and rearranging, we have, because here we are going to neglect the distance between these two, we consider these two as coinciding with respect to one another. See what we are going to have. If you substitute the values, you are going to have this equation: mu1 by PO plus mu2 by PI is equal to mu2 minus mu1 by PC. Now you follow this step Arrange all the values here. In place of I, substitute the value as alpha plus gamma and R as gamma minus beta. And we have alpha, beta, gamma values substituted. In place of M, please keep P. You will get this equation. Applying sign convention with values PO equal to minus U, because from pole, if you move towards object, you are going from right to left, but incident ray is moving from left to right. So object distance is taken as a negative, but image distance is taken as positive. R is also taken as positive because you are moving from right to left, left to right. So if you have the values here, you're going to have the equation as mu1 by minus U plus mu2 by V is equal to mu2 minus mu1 by R. It is a very important 3-mark derivation, so please follow the procedure. Refraction at convex surface, again from rarer medium to denser medium, but here we are going to form virtual image. The previous case is for real image, this is for virtual image. Procedure is the same. Whenever you want a virtual image, actually always you have to keep the object very close to the principal axis. So when you keep here, what happens? This is the refracted ray, right? This is another refracted ray, that is OC is another refracted ray, and A, from A, if you see this one, this is the refractor. Both are diverging. When they are diverging, what we are supposed to do? We have to extend them in backward direction. When you extend them in backward direction, here you are going to form the image actually. So again the same procedure. If you see, this is angle of incidence, and this is alpha, this is beta, and this is gamma, this is R, and this is I. Same procedure. If you follow, you're going to have the equation as mu1 by minus U plus mu2 by V equal to mu2 minus mu1 by R. Same procedure. Now again, if you consider refraction at a concave surface, now I am taking the second surface. Instead of convex, we are going to consider the concave surface. I repeat, procedure is the same, but here we are going to obtain the condition for virtual image. If you see the diagram, you will understand. Now this is the convex surface. Now here I am going to consider the object, and this is the incident ray, and this is the refracted ray, first refracted ray. Now this is the second refracted ray. Both are diverging, so if you extend them in backward direction, both will meet at this particular point, and this is the virtual image. In case of concave surface, again same procedure. This is R and this is I, alpha, beta, gamma. Use Snell's law, find the values of alpha, beta, gamma by using tan. We'll get the concept. And rearrange and you substitute, you're going to have the expression as mu1 by minus U plus mu2 by V is equal to mu2 minus mu1 by R. Refraction at convex surface from denser medium to rarer medium, that is forming real image. This is the case. Now if you're going to consider this, now here the object is present inside the denser medium. Now it is going to emerge out when it undergoes refraction. It is going to converge here, so real image is going to obtain. This is the first incident ray, first refracted ray, second incident ray OM, and MI is the second refracted ray. Both are meeting here, so you're going to have the real image. Incident ray makes an angle alpha with respect to principal axis. Refracted ray makes an angle beta with respect to principal axis, and normal makes an angle gamma with respect to principal axis. Incident ray making an angle I with respect to normal, refracted ray making an angle R with respect to normal. Again same procedure. Distance is U with respect to object from pole, distance is V from image to pole. Now if you apply the condition again, you're going to have the equation as mu2 by minus U plus mu1 by V is equal to mu1 minus mu2 by R. Remember this. Refraction at convex surface. Now we are going to have virtual image, again from denser to rarer medium. How the image will be. The condition is again the same. Mu2 by minus u plus mu1 by v is equal to mu1 minus mu2 by r. Now refraction at concave surface from denser to rarer medium forming virtual image. The condition is mu2 by minus u plus mu1 by v equal to mu1 minus mu2 by r. So all the conditions are similar, but you have to follow the procedure. Any one condition can be asked in the examination for 3 marks, so you have to follow the procedure what we have followed in the first derivation. Note: expression for object in rarer medium is the same for whether it is real or virtual image or convex or concave surface. Remember this. That is mu1 by minus u plus mu2 by v is equal to mu2 minus mu1 by r. So this expression will remain the same whether it is a real or virtual image if the object is present in a rarer medium, whether it is convex surface or concave surface. If the object is present in the rarer medium, whether it is real or virtual, whether it is convex or concave, this is the condition you are going to obtain. Expression for object in denser medium is the same for whether it is real or virtual or convex or concave surface. This is the expression mu2 by minus u plus mu1 by v equal to mu1 minus mu2 by r. You can see the difference between these two. Object rarer means this is the condition. Object denser medium means this is the condition. Whatever the image it may be, whether it is a real, virtual, convex, concave, whatever the surface it may be. However, the values of u, v, r, etc. must be taken with proper sign convention while solving the numerical problems. So you have to consider the sign convention when you solve the numerical problems. The refractive indices of mu1 and mu2 get interchanged in the expressions. Be careful regarding this. They may get interchanged.